any models, we usually follow this format. So I'd like to kind of review this again. So first of all, we start with the data. So what type of data we are dealing with for any particular problem. This is always kind of an important part of the any machine learning algorithm. So in particular, we would like to know what's the dimensions of the input data sets here. So that would be X superscript I here, represent the I sample of the training data sets. And whether X, what's the dimensions of the input features we have. So I represent it with Rn here. This is a kind of generic representation and indicating that the input is going to be an n-dimensional vector. Essentially, it contains n features. And the other variable we use this Y represent the target variable that we're trying to predict. So it depends on the problem we are trying to deal with. So Y can be high dimensional, can be continuous, can be categorical. So in the context of linear regression, so Y will be a continuous scalar, will be single number. So that's really I indicated with R here, represent the target in this. Right now we are considering is going to be a continuous number. And overall, we assume we have M samples indexed by I. So that's really we have I goes from 1 to M here. The total number of samples is represented by lowercase m here. So that is the kind of notations of my input data sets here. So most of the time in this lecture here, I stick with this type of notations here. Just so next time we'll probably explain less on regarding the notations here. So so sometimes here I just want to make a comment here. X here, I could put a superscript on the X as well. So I have Xi here, and I put a subscript here, J here. So that represents J's feature of the I sample. So if I want to make specifically mention that. So that's really will be a difference between superscript and subscript here. So just keep in mind with the difference here, all right? So this is the input data set here. And the model I have right now for the linear regression will be simply linear combinations of features. So that's represented in this part of that. So will be the theta dot x here, that represented as a dot product between the two vectors. So x is an n-dimensional vector. Theta is a vector of parameters. So more specifically, will be write down as in a prediction here will be theta 1 times x1 plus theta 2 times x2 plus theta n times xn here, because I have n features. So in general, I might have a bias term or intercept theta 0. However, in the last lecture, I mentioned that I'm going to change my notation, augment my features, so that the first features of my input here is always be a constant 1. So as a result of that, I'm going to follow that convention. So I will not write theta 0, but keep in mind that I always have this intercept or bias term within my models. So, however, I will simply write down as theta dot x here, or write down as theta transpose x here. So that means the same thing here. So this will be interpreted as a matrix multiplication. That will be a row vector, the column vector, row vector times a column vector. This will be a dot product between them. So sometimes I use those two notations interchangeably, but just in the context, you might understand what they are meaning. So that's what's written in this part over here. All right, so this is a, oh, sorry. So that's the model I have here, would be linear model, would be linear combinations of the input features of that. And then the next step would be how to construct a loss function to evaluate the quality of your models, because eventually we will need to learn the parameters of the theta here. And we want to identify the parameter theta such that the prediction will be very close to the actual observation y here. So now you have y hat here represent your prediction. You have y represent your actual observation. There's difference between them. Most of the time they are not exactly the same. I want to measure the difference between them in terms of this MSE squared loss of that. So that was written in this case here. And that's for one sample. So usually in this, throughout the lecture here, we usually refer to, start with describing the loss for one sample. And then next we're going to talk about loss for all training samples. And then most of the time, loss for all samples here will be simply the average of loss for individual samples. So that was written in this case here. So y superscript j minus yj here, that would be the error for one sample, for J sample, and take a square of that, that's the loss for that sample, and average over JM samples. So that would be the MSE, mean squared error, for the entire training data set. So that is my loss function. In the end, this function here will be, you can kind of understand that, and this is simply a function of the parameter theta, because all rest of them you have the values, right? Because you know to calculate the y hat here, so that would be simply the dot product between theta and your input feature x superscript j here. And both xj and yj are given to you in the training data set. The only thing in the end, if you look at the entire function here, the only thing is unknown is that parameter theta. So overall, you can view this loss function as a function of the theta only, because all rest of the data is known. You can plug in the calculated values of that. So that's the loss function. So we need to come up with a way to measure the quality of your models, evaluation purpose. The next step will be the learning step here. Once you have a loss function, and then in general, in many cases, we formulate learning as an optimization process, We want to identify those parameters, theta star, such that minimizes this loss function L theta here. So in general, because theta is n-dimensional, you have a theta 1, theta 2 plus theta n, so they have n variables. So in general, this is going to be a multivariable optimization problem. The question is, how do we solve this problem? So in general, this type of problem is not easy to solve. It's hard. And then the question is, how do we solve them? That's the actually learning algorithm is trying to do, try to solve this problem. Right? But however, I just want to mention this general framework. Start with the data, and then next we say, what's our models here? Right now we stick with linear model. Next step will be, how do you formulate the loss function? Right? Loss function would be a single function. Evaluate the quality of your models. Typically, it's a function of the parameters of your models. So next will be learning. Learning will be an optimization step. Try to identify the optimal parameter that minimizes the loss function. And that's what we do. So next I'm going to talk about how do we solve the learning problem. So but before I solve the learning problem here, I just want to mention another